Okay, students, we're going to go ahead and review Chapter 6. So in 6.1, that's where we learn the basic rules for finding the areas under a standard normal distribution. And we always use Table E to look up these areas. So for example, our first rule, whenever we want to find the area to the left of any z-value, all we do is we look up that z-value in Table E, and it's going to provide us with the area to the left. Now, Rule 2 tells us if we want to find the area to the right of any z-value, we look up the area in Table E, but then we subtract it from 1. And then finally, if we want to find the area between any two z-values, we have to look up both areas and subtract the smaller area from the larger area. The result should be a positive area. So that's the basis of our Chapter 6. And sometimes they have us reverse the process, so to find a z-value when we're provided with a given area, what we have to do is we have to get the area all the way to the left and then use that area to look up the z-value. So for example, let's say that we were provided this problem here. We want to see the z-value that corresponds to this given area. It's between the z-value and 0, and they tell us that the area is 0.4505. So our first step is we need to find the area to the left of the z-value. So we take, since we're only working with half of the normal distribution, you take 0.5 minus 0.4505, we have 0.0495. Then we turn to Table E, and we're going to look in the negative z-value since we're on the negative side of the z-values. We look up 0.0495, and you'll see that it is the z-value, negative 1.65. So this first portion is just a review of what we did in 6.1. Now in 6.2, that's where we start applying the normal distribution to problems involving probabilities. And there's a step-by-step process we follow. Step 1, we draw the normal distribution and write down the mean and standard deviation. Step 2, we shade in the desired area that represents the probability, because now the areas represent probabilities. We convert x values to z values, and we represent a z-axis below the x-axis. And then we will use the formula z equal to x minus mu over sigma to make this conversion. Always round the 2 decimal places. Finally, we use the rules that we learned in 6.1 to find that missing area. So let's take a look at an example. Let's assume that the Physics 101 exam scores are normally distributed. The mean is 74 and the standard deviation is 9. Compute the chance that a student will score more than 85 on the exam. So here I have the standard normal distribution. We're first going to convert using our z formula. We will convert 85 to a z value. So 85 minus 74 divided by 9 is 1.22. So we want to find the area to the right of 1.22. We look up 1.22 in Table E, we get 0.8888. That's the area to the left. Since we want this area to the right, we just subtract it from 1, and we have the answer, 0.1112. Now the other concept that we have to perform or learn about in 6.2 is the reverse process, where we have to find the cutoff score. So the steps for finding the cutoff score is we draw and label the normal distribution, shade in the given area, use the areas to find the z-values that correspond with the cutoff scores, compute the cutoff scores using our cutoff score formula, and then finalize the results. So let's assume that a Physics 101 exam scores are normally distributed. The mean is 74, standard deviation is 9. Those students who score in the top 5% receive A's on the exam. What is the cutoff score to be in the top 5%. So this area on the right side represents the top 5%, or 0.05. We take 1 minus 0.05 to get 0.95. That's the area to the left. So what we now do is we look up 0.95 in our table E, and we find that the z-value will be 1.65. Then we're ready to compute the cutoff score. Using our cutoff score formula, the mean is 74, the z-value is 1.65, the standard deviation is 9. We calculate this, we end up with 88.85, which rounds to 89. Thus, a student will need to score 89 to receive that A in this Physics 101 course. Now, that was 6.2, so these concepts are 6.2. Now we get to 6.3, the central limit theorem. So let's go ahead and determine the central limit theorem. To do this, we are going to use a new type of z-score formula. So we say the distribution of sample means is used whenever we desire to find the probability that involving the mean of a sample. The key to let us know that we're going to work with the distribution of sample means is that we're going to be given a sample size of n. Okay, so let's look at an example. Assume that the time to find a parking spot, we'll say at a local university, is normally distributed. The mean is 15 minutes and the standard deviation is 6 minutes. If a sample of 30 drivers trying to find parking is randomly selected, then compute the chance that the mean of the sample will be less than 17 minutes. So the clue here is we're given a sample of 30 drivers. That tells us we're going to be working with the distribution of sample means. So we have to use this conversion formula. X bar is the mean of the sample of 30 drivers. So we're going to put, and that's 17 minutes. So it's 17 minus the overall mean of 15 divided by standard deviation of 6 and a sample size of 30. Now, when we're performing the calculations, 17 minus 15, always do that first, you get 2. And then to make it easier, take the reciprocal of 6 over radical 30. So it's 2 times radical 30 over 6, which is 1.83. We rounded 2 places. Now all we have to do is look up 1.83 in table E, and we get the answer, which is 0.9664. So these are all examples of what you're expected to know for sections 6.1, 6.2, and 6.3. Take care.